I like to draw some figures, and I don't want to use slides. Okay, Q is the shear flow, and tau is the average shear stress. And before I put into detailed calculation or explanations, and here I directly give you certain the rules. Okay. So for example, if we consider a cross section, any type of the cross section, and usually we would have the open like this, or we could have what we call a box thing. More or less, we can see the cross section will be something like the Q. Okay, so this is called a box beam, and this is just general. And assuming if we have determined the transverse loading, for example, here I demonstrated is in the vertical directions. Then by all means, the first step in your calculation is to determine the centroid, and then passing through the centroid, you draw a line perpendicular to the direction of the transverse loading. This will give you the definition of the neutral axis. For this one, the centroid is here. Then you draw the direction, you draw a line perpendicular to the direction of the V, that is the neutral axis. And now we come to determine the directions of the shear. In the dimensions, in the geometry of the cross section, and in the same direction of the V, the transverse loading, the shear stress is to align in the same directions. Okay, so that means on the two sides, the shear stress, direction of the shear stress or shear flow will be in this way. And how about for the horizontal portions? And that one is to take up the concept by maintaining the continuous flow of the shear. Okay, and there's no break. So that means from here you can see we have to, the whole thing, if you would think about this, will be the flow of the fluid. So it seems like the fluid will be converged to here and moving down and then diverge to there. And that is the way it's like. Okay, here I directly summarize the rule, but I will explain why. So here in this way, the shear will be like this. And starting from here, this side is 0. Basically, the shear stress on any surface will be 0. Okay, and here is 0. Okay, the shear stress on any surface will be 0. For this case, again, we want to maintain the shear flow. So basically, the shear flow going to here, and they're going to converge to here. And basically converge to this point and diverge from this point and then move around. So here, this point is a 0 shear stress. And the same thing here, this point has a 0 shear stress. And assuming here the box beam is symmetric, this has the width of plane of symmetry. So basically here, let me draw the principal axis for this case. XY. Basically XY are the principal axis of this given geometry. And so from here you can see basically 0 tau, basically if I extend it, this diverge from here, converge to here, going to 0. Starting from 0, converge to 0 here. And here is the direct summaries of today's lectures. And this one pretty much, you don't have to, this rule sometimes can help you to calculate the province. And I will use a few examples to demonstrate, but let me explain why we can use, and let me use a few examples to demonstrate this one here. First, let me look at this one, and this is not a box, it's an open geometry, so let me draw this one here, and put into 3D. Okay, three-dimensional look like something like this one. And for example, assuming here transverse loading is applied in the vertical directions. Okay, that is the direction of the transverse loading across these cross sections. So in other 2 dimensions, then you draw the cross section into the So now the first step, again, we identify the centroid. And this is the direction of the V. So from here, we identify our neutral axis. That always be the first step. And now I want to show you the direction of the shear flow for this case. For example, in our exercise, we always work on the 2 dimensions, and here the reason why I have explained earlier. This one, usually, for example, here, say if I want to say consider the point here. So basically, what we did is we make a cut. Okay, here I do this way. So here we selected this is our shaded area to calculate Q. So the shear flow will be equal to VQ over I. Here the V is the given the transverse loading, and I is the moment of inertia. Of the entire cross sections about the neutral axis. And Q, basically for this case, Q is equal to, for example, here if we be able to measure the centroid of this shaded area, let me call the Y bar, and this area, let me call the A. And so basically Q equal to A bar times A times Y bar. Okay, for the shaded area.